Hello everybody and welcome to the second A2 Chemistry Carlam Cymru revision session for 2023. This session this evening will focus on acid-base equilibria, specifically the typical approach to exam questions and exam techniques. And this evening session will be presented by Mr. Black from Penglai School in Aberystwyth. Now the session will last around 45 minutes when Mr. Black will run through the relevant content with you. Now, if you have any questions during the session, please use the Q&A section and we'll do our best to answer you. Now, you will see that there's also a hyperlink in that Q&A section. If you're happy to leave your name and email address, we'd love to hear from you and keep in touch with you so that we can send you any information about the future events. You can click on that link at any time during the session itself. Now, today's session will be recorded and the recording and any relevant resources uploaded to the e-sgol website under the Carlam Cymru tab. So thank you, Mr. Black. It's over to you.
Okay, thank you. All right, so 3.9, if you've seen the advanced notice, you'll see this is one of the key areas that's going to be questioned. Can put people off this topic, acid-base equilibria. Looks like lots of complicated maths, but actually it's quite easy. What I like about these questions is they don't really vary from year to year. So you think about calculations in year 12, they can ask you anything in any way they want, whereas these are pretty straightforward once you know how to do them. So let's get started. So what I've done here then, I've done a summary of the calcs that you kind of need to be good with. I'm obviously going to go for the PowerPoint and work, show you how they're derived and how we use them. But I thought we'd have these up here for you. So these are all the sort of formulas you're going to need to be able to use and manipulate. And I've got this one here as well for buffers. So we'll have a look at these today. And then I've got this one here. And, as we go through the PowerPoint, we'll be explaining what they are. HEP is for half equivalence point. Now, I've put them in at the start. I did put them in at the end and I thought, well, I might not get to them. So once you've watched the presentation or gone through the PowerPoint, perhaps go back just to hammer in these expressions. Okay, so we'll start off with what's an acid. Well, if you went to GCSE, you know it's something that forms H+ ions in water. Great, good, all fantastic. You'll notice here, we'll talk about this species later. So what we've got there, that represents the dissociation of a strong monobasic acid. And what monobasic means is it only generates one hydrogen ion per molecule. Okay. Dissociation is a term we use for when it generates those hydrogen ions. You'll notice the arrow here. It's going in one direction. Strictly speaking, it should be reversible, but being a strong acid, they fully dissociate. So I tend to use an arrow in one direction for a strong acid. Okay, and I was going to mention the H3O+ because hopefully you're all familiar with that, the oxonium ion. And that's because protons aren't going to exist in water as protons. All right, got a positively charged particle. You can see here it's formed a dative bond to the H+ ion and you end up forming this H3O+ ion. Okay, and you can see the dative bond symbolized with the bond that you typically see, but with the arrow pointing from the species that's donating both electrons to the covalent bond. Okay, now we have diprotic acids as well, and sulfuric acid is the most obvious example of that. And what you can see is that the acid can generate 2 hydrogen ions per molecule. It can actually do it in 2 steps. Okay, but we can just sum it up as the 1 step here. I don't know why I've got that 2 there, actually. It's a bit random. We've got that off our website. So, yeah. So H molecule of sulfuric acid. That 2 shouldn't really be there. Each molecule of sulfuric acid generates 2 hydrogen ions. Okay. Now, A level. Definition of an acid. Really, you need that Lowry-Bronsted definition. So, as you can see in this reaction here, we can see, for example, we've got this species, so this could be water, and this is our ammonia, and you can see how the water is acting as an acid. It's lost its proton, and the ammonia is acted as a base by accepting that proton. Now, these are terms that we get at year 13. Don't tend to really talk about them in year 12, and they're quite important terms actually for year 12. So your acid, because this is a reversible process, if we went back in this other direction, you can see that the hydroxide ion that's formed from the water in this direction acts as a base. So the species you form from the acid becomes what's known as the conjugate base. And if you look at the base, which forms this ammonium ion, you can see in the reverse process, it's regenerating NH3 by donating a proton. So this is the conjugate acid, and I think this is probably the most important term. This is the conjugate acid of the weak base ammonia. All right, so you need to view it in both directions. So that's your Lowry-Bronsted definition. Really important that you can talk about Lowry-Bronsted acid as being a proton donor and the base as being a proton acceptor, and perhaps being aware of these terms here in year 13. Okay.
Sorry, can I just ask a quick question for you, based on your previous slide there? That's just a quick inquiry that's just come in. You said that there was a H+ ion that was allowed in the kind of breakdown or dissociation of the acid. Would you be allowed, because it's aqueous, to represent it as H3O+ and an OH- because of the reaction that can take place?
Yeah, you would be. I mean, without looking at Mark's scheme in front of me, they're the same term. So generally we tend to use it. For example, when you look on a Ka expression, you see it written as H+, or you can see it written as H3O+. So yeah, chemists kind of recognise that the species is H+, but it will exist as H3O+. Always though, always check your mark schemes. I know my mark schemes pretty well, but don't quote me. But yeah, I would say H+ is absolutely fine. But if they asked you to show its dissociation in water, I would show it as H3O+, because I'd want to show the water there. So I hope that answered the question. Okay, so just going back here, the ammonium ion, again, just shown in that species, just because chemistry, it's just so interlinked and so many different things come in. Just shown again, this is the ammonium ion, and you can see this dative bond here with the lone pair for nitrogen. Okay, so that's how the ammonium ion forms. And yeah, there we go. I'm so tempted to go off on off piece and start talking about CPR, but I'm not going to. Okay, so what is pH? Well, it's quite a hard thing to express. I'm going to talk to you about how to talk about pH in the exam. So pH is a measure of the concentration of hydrogen ions in a solution. And the thing about hydrogen ions and acids is that value can vary massively. It just depends how well your acid dissociates. So we tend to do, and we talk about, acids dissociating. We use a logarithmic value for our hydrogen ion concentration. And if you look on mark schemes, one of the things I'll ask you in the exam is to define pH. You may scratch your head at that, but it's actually really easy, Mark, because all you have to do is write that. That is how you define pH. All right, and you can write a sentence about it, but why bother? Just literally write the expression for calculating pH. So that's how it's defined. And we're talking about how we use that expression in a minute and where these values come from. So monoprotic acids, this value here is quite important to know what how many hydrogen ions acid will generate. So for example, if you've got a monoprotic acid like hydrochloric acid, you know that for every one of those molecules, you will generate a hydrogen ion. So you can assume for a strong acid that the concentration of hydrogen ions will be the same. And same for diprotic acid, only now we generate 2 hydrogen molecules per molecule. So hydrogen ions per molecule. So for example, if we've got a 0.1 molar solution of sulfuric acid, hopefully from year 12, you'll recognise that this is going to generate twice the number of hydrogen ions, and therefore its number of moles is twice the value per litre. Okay, this is really important for when you're calculating pH. So let's look at how we do that on our calculator. So to calculate pH, just make sure you know where your buttons are. Don't buy a new calculator before the exam, because you're just asking for trouble. So there's your minus button that you want to be using, and there's your log button. Okay, so you just literally type in log, that's your log base 10. So log and then minus whatever your concentration, or sorry, minus log and then whatever your concentration is. So if you have a look here, then there's our expression for pH. So for example, if you've got a monoprotic acid, like nitric acid, then we would literally type that into our calculator, minus log base 10 0.25, and we get our value of 0.60. Usually we like to quote pH to 2 decimal place values. Here we've got sulfuric acid. So how are we going to work out pH here? Well, this is the trap, and examiners invariably ask for the diprotic acids because they want you to make sure that you use the right value for the concentration of hydrogen ions. So you can see I've doubled the concentration of the actual acid itself, and I've done my minus log base 10. That gets a pH of 0.70. Okay. The other thing that they might ask you to do, and I'm going to talk to you about this actually in another context in a minute, is calculating the concentration of your hydrogen ions if you're given a pH value. So it's the reverse of what you've just done. Okay, so that's how you work out pH. So the opposite of that, which is where we're trying to work out H+, we just do this. Okay, so we take the inverse log. I'm going to show you on your calculator how you would do that then. So let's say we've got a calculation where we're asked to work out the concentration of the H+ ions with a pH of 1.6. Okay, so that's what we do on our calculator. And just to show you what that would be like on your calculator, first thing you do is you press your shift button. Okay, then you press your log button and you'll get 10 to the whatever power. Okay, and then you press your minus and you type in your pH value. Okay, and if you did that on your calculator, you'd come out with an answer of 0.025. Always quote units if it's not there, moles per litre or decimeter cubed. Okay. Now, you can never tell what examiner's going to ask you. They may ask you, not for the H+ concentration, they may ask you for the concentration of the actual acid. All right, so for example, I'm on a basic acid like HCl. So you can see what I've done is I've just literally done the calculation like we've done earlier. I've worked out my H+, and we're going back to that principle that for every mole of H+ ions, with them on a basic, the concentration of the acid will be the same. And then where it gets a bit trickier is where we look at a dibasic acid. All right, so for a dibasic acid, oh God, I can't believe that 2's still there. Don't know why it is still there. It's a real pain. Be careful what you lift off the internet. So for a dibasic acid, for every mole of 2 moles of hydrogen ions that you generate, this will be half that value. So let's have a look at, let's go back. Let's have a look at that calculation. So you can see here, I've done worked out my concentration of hydrogen ions as 0.025. So just literally doing the same thing, 10 to the minus, okay? And then what I've done is I've halved that value, and it goes back to this relationship here. For every mole of this generated, half a mole of that was needed, okay? So that it deals with your concentration. The other thing as well, sometimes people get a little bit thrown off when they see the pH is above 7. Does make a difference. You do the same thing, okay? So you literally would work out your hydrogen ion concentration using that principle there, okay? So again, you can just see I've done the minus 12. That's my minus pH. Now, you're probably looking at this and going, what's going on here? We're not doing rate, but it's quite important to know if you're doing a rates question and you get a question about pH, one of the constants, that's actually telling you concentration of hydrogen ions. Now, in this case, it's actually really easy because the pH values are, integer values, and you should know on the pH scale that when you go up the pH scale, so when we go from 0 to 1, the concentration of our hydrogen ions decreases by a factor of 10. Okay, so that's one way of doing it, just literally looking at your pH scale and actually just merging into the whole rates of reaction kind of thing here. If we look at what's happened to our rate, the one thing that sticks out in my head here is this run here, run 1 and run 3. And you can see that the rate's changed by a factor of 10. So this rate is 10 times slower. And if we have a look, we can see our pH has changed by 1. So the H+ concentration has decreased by a factor of 10. And that tells me the H+ ions affect rate. And the rate is that change is proportional. So I know no H+ ions are proportional to rate. Okay. So yeah, just a little thing for you there. By the way, just pointing it out, the Fe3+, 0 order, that's also changed, but it's had no effect on the rate. So yeah, they can throw pH at you in the exam and the kinetics. And the other thing I was going to show you is that, if they're not whole values, then you'd have to then work out your H plus concentration, which is literally where you do the inverse log, okay, of the pH value. There we go, and you can see again this is 10 times weaker. Great. Okay, now the next one we're going to look at, probably when you've been taught this topic, you've done the these calculations, and the one thing I'm going to stress to you 100% here, by the way, your hydrogen ion concentration, you can only assume that it's the same as the concentration of the acid when it's a strong acid. All right, that's very, very important. We'll talk about weak acids later. Now, the next bit, this is important for us. This is about the dissociation of water. So we can see here how water has broken up into two separate ions, the hydroxide and H plus ion. It's a reversible process, so I don't like that arrow. And we can express it as a Kc expression, I guess. Okay, so we've got the products multiplied together, divided by the concentration of the reactants. Okay, but actually you'll see it written like this. They ignore the water. All right, and the reason for that is it's such a massive value that even if I was equilibrium so far over this side that even if I was to, you know, change this by a factor of 10, this hardly changes at all. So it's just treated as a constant. So typically we don't write it like that. We write it as what's called Kw. And this is a very, very important expression for us. And so is this value here. In fact, it's quoted on your data book, Kw. Okay, now the next thing is you'll see that I've specified this is at a particular temperature, 25 degrees C, and you'll see why that is in a moment. Okay, so the next thing I want to tell you is that in pure water, for every mole of H plus ions you generate, of course, you generate equivalent number of moles of hydroxide ions. And this means that in pure water, these concentrations are always going to be the same. Okay, and that is the definition of what we mean by neutral. And that's very important you know what neutral means. You might think neutral as being pH 7, as you're about to see. It isn't. Neutral is when your concentration of hydrogen ions and hydroxide ions is the same. Okay. So, for example, if our Kw comes out as 10 to the minus 14, we know the concentration of the H plus ions is 10 to the minus 7, and the hydroxide is also 10 to the minus 7. Now, therefore, you can see here what I've done, just a quick calculation. I've done my minus log base 10 of the H plus concentration, and you get your pH of 7. So it just so happens at 25 degrees C, where we've got this Kw value of 10 to the minus 14, our pH comes out at 7. Now, here's a question for you, and it brings in equilibria. Okay, so we've got a different temperature. We've got 40 degrees C, and have a look at what's happened to our Kw value. What does that tell us about this reaction then? Have a quick think. I'll just do something. Wait a second. Okay, so if you look at Kw, we've got a greater value, and that suggests to us then that the concentrations of these species here have increased. That means equilibrium's moved in this direction with the higher temperature. And hopefully you know from the Chatela's, increase in temperature favours the endothermic direction. So that tells us the dissociation of water is an endothermic process. Now, let's look at what's happened to pH. Okay, so the first thing we'll do is if we want to know pH, we've got to work out H plus. You're going to get bored of me saying that today. So we're going to find our H plus value. So we're going to look at our expression. Okay, we know Kw at this temperature is 2.09 times 10 to the minus 14, and that's equivalent to the concentration of the hydrogen ions and the hydroxide ions multiplied together. And what we know, as what we said earlier, is in pure water, these values are the same. So effectively, we can say it's H plus squared. Okay, and then hopefully you can see how you can work out your concentration of hydrogen ions. So we just take our Kw and we square root it. Okay. So if I square root that to get rid of the squared, I square root that. Now we got our H plus, which comes out as 1.45 times 10 to the minus 7. And now we plug it into our calculator as minus log base 10 H plus, and we come out of a pH of 6.84. So is water neutral at this 40 degrees C, at this higher temperature? And you're probably thinking, no, it's not pH 7. Yes, it is, because neutral is when you have equal concentrations of H plus and OH minus, which we still have. We've only moved equilibrium in this direction, right? So we have more of these H plus ions, so we've got a lower pH, but we've also got an equal concentration of these being generated. For every one of these, extra one's made, an extra one of these is made. So just learn pH is when the H plus and OH minus ions are of equal concentration. Okay, now the next bit, Kw. Why is it important? Well, I think Kw is more important for actually calculating the pH of a strong base, and this will only work for a strong base, by the way. Okay, and the reason for that is you can see here, and I'll just do that again. I can rearrange this expression that I can work out my concentration of H plus ions. So as long as I know Kw and I know the value of my concentration of my hydroxide ions, I can calculate my H plus, and then that allows me to calculate my pH. So a little example here, calculate the pH of 50 centimeters cubed, 0.1 mole of sodium hydroxide. So when I look at my expression, I've rearranged it to find H plus. That's my Kw. So we're assuming here this is at 25 degrees C, and because it's a strong base, we can assume that the concentration of hydroxide ions is the same as the concentration of the base. So when we do that expression, we get a pH of 13. So you can see here I've worked out my H plus, then I've just plugged it into the pH formula. If you've got a strong base, it's like your sulfuric acid. For every mole of base, you've got twice the number of moles of hydroxide ions. Okay, so you can see here what I've done is I've taken the concentration of my base 0.2, but I've doubled it because for a mole of barium hydroxide, 2 moles of hydroxide ions are produced. You can see there we get a different pH, a higher pH, of course. There we go. Right. Now, weak acids, as I said earlier, our equation where we were doing minus log base 10H plus. For strong acids, we could simply assume that the concentrations were equivalent. Okay, we can't do that. The only with weak acids, only we could do that with strong acids that they fully dissociate. So for every molecule of HX, you would generate the equivalent number of moles of H plus for a monobasic. Okay, whereas a weak acid, they only partially dissociate, and in fact, it's very, very small how much of those ions acid molecules dissociate. Typically, like I think ethanoic acid, they quote 3% of them dissociate. So what we can't assume is that our H plus concentration is the same as the concentration of the acid because it's far, far, far lower. So we'll look at how we do this then. Now, just to point out to you, I'm sure you're very familiar with this concept, but make sure you know how to describe a weak acid and a strong acid. So what I've got here for you then are some examples of strong acids and weak acids, because you need to be able to discuss strong and weak acids. I was, funnily enough, talking to my A-level chemist today. We were just going back and looking at phenols, and I thought, well, if I wanted to quote a weak acid and I was a bit bored of talking about carboxylic acids, I might chuck in there phenol, because as you know, it's a weak acid. So there you go, it's an extra one for you. And then what I've got here as well are some strong and weak bases. Okay, so your strong bases, you know the sodium hydroxide, your potassium hydroxide, so like your group 1, group 2 hydroxides. A really good one to quote for a weak base, and I'll probably be quoting it a lot tonight, is ammonia. But then you've got your amines as well. Okay, so they're good examples of your weak bases. And one thing that I always kind of point out to my students, oh, there you go, there's your strong acid base, fully generating hydroxide ions, and there's a weak base. Okay, so that's how you'd represent a weak base in water. And that is a question that comes up occasionally and always catches people out. And it's this question that says, describe a weak base. So people don't have a problem with weak acids. They can say, no, it partially dissociates. But make sure you've got a good definition of a weak base, because it sometimes is asked for. Either of those will do. A species that sets H plus or a species that releases OH minus in a reversible reaction, as we can see here. Okay. Right. So how do we find the pH of a weak acid? Okay, well, we're going to go to the idea here that I've mentioned, that H plus is not equal to HA. By the way, HA, I'm sure you're familiar with it, but I'll just assume you are. that refers to the concentration of your acid. All right. So, for example, 0.1 molar HCl. And we can't assume that here because only partially dissociate. So what we're going to go to then is we're going to have to write out the equilibrium law for a weak acid, and this is our go-to. Whenever I'm doing a calculation with A-level chemists on acids and I'm not quite sure what formula I'm using, I always go to this. So really, really good start off point to do your calculations. So what you can see here is we've got our Ka, our acid dissociation constant, is equal to the concentrations of the H plus and the conjugate base that it generates divided by the concentration of the acid. So we'll look at a calculation with that now. Okay, so now what I've done there, and I can't quite see it, so my screen's a bit different to yours, but what I've told you at the top there is that what we can assume is that for every mole of this generated, IH plus, an equivalent number of moles is this generated. So these two values at equilibrium will be the same, and therefore to make our lives easier, you can see that I'm writing an expression like this. So I've squared that value. And what I'm trying to do here to get to pH is I'm trying to work out H plus. Okay, so the first thing I've done there is squared that. And the next thing is I'm taking that over there. So on that side I was dividing, so here I'm multiplying. And then finally, I need to get rid of that square on the right hand side. So we're going to take square root of both sides and we get that expression there. Okay, so that's quite important. Make sure you know it. But I also think, you know, it's not a bad idea to be able to rearrange to find these expressions because it's not that difficult. Okay. The HA value, as I say, is the concentration of the weak acid, and we can assume that is this, you know, what's quoted in the question because they don't really dissociate, so very little of it has actually gone. So let's have a look at an example. So we've got a Ka value here of 1.76 times 10 to the minus 5. Now you'll notice that's a very, very small value, and we will look at Ka values in a second. But if you think about the equilibrium, what that's telling me, a very, very small value like that, is there's very little of these species and lots of the undissociated acid. We'll go back to there, and we're trying to calculate the pH of the solution, and we can see here that it's got a concentration of 0.220 moles per decimeter cubed. Okay, so we're going to work out H plus because that's how we work out pH, and that's the expression we've rearranged earlier. So if we just have a look, there's my Ka, 1.76 times 10 to the minus 5, multiplied by the concentration of our weak acid. And that gives me a concentration of hydrogen ions there. And then all I do is minus log base 10 that. And what I get is a pH of 5.41, which is sensible, right? It's below 7. You know, that's always a good thing. If your pH comes above 7, you've done something wrong. So there you go. So here's another kind of question we've got from the exam. We're going to work out the the Ka expression for HF. Tells us it's a weak acid. Okay, so we can write that out. And I think I got asked a question earlier about, you know, do you write the H3O plus? You can see here I haven't, so that's a good indicator to you. I think the only time I would put H3O plus if it specifically mentioned water. Okay, and there's my Ka expression, products over reactants. So we're going to calculate our pH. So H plus is the square root of Ka times HA. The HA was quoted as 7.20 times 10 to the minus 4. The concentration of the acid, can't see where it is. Oh, there you go, 0.10. So now I take my minus log base 10, because this is my H plus concentration, and I come out with a sensible pH again of 4.14. So yeah, you can see here, kind of worthwhile knowing what Ka tells you. Ka is telling you how far equilibrium's lying to the right hand side, and the smaller the number, the weaker the acid. Okay, so you can see here that we've got acetic acid, which is like vinegar, ethanoic acid to you, 1.75 times 10 to the minus 5. And then we've got these really high pHs like hydrochloric acid, hydroiodic acid. What I didn't know about hydroiodic acid is that it's a stronger acid than hydrochloric acid. And the only reason I know that is I can see my Ka value is massive. So that means there's loads of hydrogen ions being generated and very little of the undissociated acid left. The one thing you'll notice about these values is there's a massive variation in them. So one of the things we do, like we just did with hydrogen ion concentrations, is we take a minus log base 10 of the value. Okay, and what we're doing is basically compressing. So you can see here, I'm just talking about the Ka values, and here you can see I've turned them into what's called a pKa value. Interestingly, the P is just like the P in pH. It means minus log base 10. Okay, so pH is minus log base 10 of the H plus concentration, and pK is minus log base 10 of the Ka value. And it's just compressed the value so we can get a bit of a better idea about what's going on. And you know, the one thing to be aware with Ka values is that the more negative the pKa value, the stronger the acid. Okay, and what I'm showing you here is how to get Ka. So if you've got a pKa value, you can turn that back into a Ka value, just like you did with pH. And this is where you perform the shift log minus pKa. Okay, so we're taking the inverse log. So those are calculations for a little bit, although they're going to come back into this because a really, really big part of the acids and alkalis is titration curves. All right, so the first thing for you to notice is, or be aware of, is the typical shapes we get. We're going to explore these shapes, but you know, make sure you kind of like got a good idea about how to sketch them. It's not just a sketch, it's a sketch with detail that you're going to have to do. So there's quite a lot of important points here. So the first thing I'm going to talk to you about is this word equivalence point. Now, what's equivalence point? Well, equivalence point is where you've added exactly the right amount of H plus ions and OH minus together so that it completely cancel each other out. Okay, and it just so happens that if you pick the right indicator, the equivalence point will match up with when your end point of a titration is. Okay, by nature. Now, the one thing I'm going to say to you here is, well, let's have a look at the equivalence point in a bit more detail. Now, the one thing that on the sketch, if I'm asked to do a sketch, is first of all, you know, if I'm given a concentration of the acid, I would be doing working out what the pH of that acid is at the start of the titration. So you can see here from this shape or these pH values, this is a strong acid being added to a strong base. Okay, so we end up with a high pH at the end. And like I say, I've got a starting pH here. I could calculate that if they gave me the concentration of the acid. So they might say, for example, 0.1 molar HCl. I would just do minus log base 10 of 0.1. Or what they could do in the exam is they could give you that curve and say, what's the concentration of the acid? So this is where you do your shift log minus pH, or inverse log of the pH minus pH. You see here, for example, I've calculated that the concentration of this acid, HCl, is 1. Okay, so 1 mole per decimeter cubed. Now, like I say, the equivalence points when we've got stoichiometric amounts of H plus and OH minus ions added. So there are some calculations that we might have to do here, because you may have to work out what volume of sodium hydroxide that equivalence point occurs at. Okay, so for example, we've got 20 mil of 0.1 molar HCl. I've specifically chosen in this example the same concentration of sodium hydroxide. So hopefully you would be able to, without doing any silly calculations, work out that would be 20 mil, same concentration. Here, I've just switched it up a little bit, and you've got 20 mil of 0.1 molar HCl. This time we're adding a base that's 0.2 molar, so it's twice the concentration. So hopefully you can appreciate you're only going to have to use half the volume. So that would work out at 10 mil. So if you're doing your sketch here, I would be doing my equivalence point, this steep section here, at 10 mil for this acid base titration. And for this one, I would be doing it at 20 mil. So when we say sketch, there's a bit more to it than a sketch. This one, this is a bit trickier because here you'd have to do a moles calculation, or I would. You may be able to do it in your head, I can't. So the first thing I'm going to do is look at the question. 0.515 mole of sodium hydroxide is added to 25 ml of 0.1 mole of sulfuric. So the first thing I'm going to do is work out my moles of sulfuric, and that gives me 2.5 times 10 to minus 3. Stoichiometry, for every mole of sulfuric, you need twice the number of moles of sodium hydroxide. Okay, so you can see there the moles of sodium hydroxide needed will be double. So I've multiplied that by 2. And then finally, I've worked out the volume using my concentration equals moles over volume formula triangle to work out the volume needed. Okay, so I've worked that out as 0.03 deciliters cubed. Times that by 1,000, it comes out as 33.3 mil. So I don't think they'd give you one like this one here. Okay, but I just threw it in there, just good practice, working out your moles of the acid, working out the using the mole ratios to work out mole sodium hydroxide, and then rearranging your formula triangle for concentration. So here we can see a strong acid being added to a strong base. It's exactly the same thing. Okay, the equivalence point, you'll notice 50 mil, 0.1 mole of sodium hydroxide with 1 molar HCl. This is why we've got the equivalence point of 50 mil. We're going to talk about that equivalence point. It's a really important idea. Oh, I'm working at the starting pH on this one. Again, this is something that we did earlier, bringing stuff in. We're going to use our KW expression. We're going to rearrange it to work out our H plus. Okay, so for us here, that would come out as 1 times 10 to minus 13. And I can work out my pH, and that starts at pH 13. So, it's the thing with titration curves is you are really applying the calculations that but not inherently. All right, they're not specifically saying things like this. They're expecting you to be able to make those jumps yourself. What kind of titration we got going on here then? All right, well, I'm looking at this and I'm not thinking it's a strong acid. I'm thinking this is a weak acid. And it looks like I'm adding a base to it, and it looks like this is a strong base. And there's various clues here that I'm going to point out to you why I think that. Okay, so it's weak acid, strong base being added to it from the burette. So the first thing I'm going to point out to you is you should be able to calculate your starting pH. Okay, so you can see here, ignore those things there, those my animations, and yeah, they shouldn't be there. It's just H plus equals your concentration of the acid and the Ka value. So if they give you the Ka value when they're asking you to do the sketch, you should be able, and the concentration of the acid, you should really work out your starting pH using that expression there. Okay, and I'm going to talk to you about this bit here. So before this bit here, you'll notice there's a rapid change in pH, and then suddenly it goes flat. So I usually show that on my sketches. So I do a rapid change in pH, then a flat section, and hopefully you guys know that's because you've got a buffer being formed. I'm going to talk about buffers, hopefully, with time. And then there's another really important thing I'm going to talk to you about here, and you quite often see this come up in exams. This is the equivalence point at 50 mil. So this is the half equivalence point at 25 mil. So half equivalence is when you've only added half the amount of the H plus and OH minus ions together. Okay, so we call it half equivalence point, or as I abbreviated earlier, to HEP. And there is a reason for this, and I could go into the detail of it, but you don't need to know the detail. What you do need to know is at HEP, half equivalence point, the pH value is the pKa value of the acid. Okay, so if they ask you to work out the Ka of your acid, it's very easy. You just go to your half equivalence point, you read off the pH, and then you convert your pKa value into your Ka value using this expression we mentioned earlier. Okay. Right, here's another one. So here we can see we've got a weak base. Okay, as you can tell from the pH, you wouldn't be expected to work out the equivalent, the pH for a weak base. Again, they're calling it the midpoint. I call it the half equivalence point. Okay, and again, this is a pKa value. All right, so this pH value is a pKa value, but what's the pKa value of is actually the ammonium ions that we're generating here. Okay, I'm going to talk to you about that now. Again, we can see buffer action occurring because we've got a weak base and a strong acid. So we'll talk about buffers in a minute, hopefully. So I've got a question here. This is from, I think it's 2017, might be 2016. pH curve, we've got a weak base and we're adding a strong acid to it. Okay, and this is ammonia versus hydrochloric acid. So you can see here I've represented that as this reaction. So ammonia plus HCl forms ammonium chloride. And I've written these as separate species because it's the ammonium chloride, if you look at the question, that we're being asked to work out the Ka value for. So you're probably thinking, hang on, this is a base. Why am I working out a Ka of the ammonium ion? Well, if you go back to the start of our lesson, if you remember, I spoke to you about this species is a conjugate acid of ammonia. Okay, so what we're going to do first of all is going to write that expression out. You can see here how the NH4 plus is actually acting as a conjugate acid, and that's why we can work out its Ka value. And it's just very simple. It's exactly the same as you said before. That kind of explains the principle, but all you need to know is at the half equivalence point, your pKa is equal to pH. So if we look at this graph here to work out my Ka value, all I do is I go to my half equivalence point at 10, and when I hit the line, I come across to the pH, and I get a pH of 9.3. So my pK is 9.3, my pH is 9.3. Okay, or more to the point, my pH is 9.3, so my pKa is 9.3, and then using that expression there, which is the inverse log of 9 minus 9.3. gives me my Ka value, which, well, you'll have to do it on your calculator. I thought I put an answer there, but do it on your calculator and you'll get, oh yeah, there's the answer. Okay, 5.01 times 10 to the minus 10. So half equivalence point, watch for it. It's a really, really useful little thing to know. And the key thing is just remember pH equals pKa, and make sure you know how to work Ka from pKa. Right, how are we doing for time? So I'm going to check my clock. Right, not too bad. I can get to where I want to get. The pH of equivalence points, very, very important. You know where they are. Strong acid, strong base, strong base, strong acid. It's where you'd expect your equivalence point to be, which is at pH 7. Okay, but it's not the case for our weak acid versus strong base. So, for example, ethanoic acid and sodium hydroxide. If you come across to the half equivalence point and halfway up, and we come across, we see typically, I usually quote 8 to 10 for the pH of my equivalence point. So you may be thinking, well, hang on, I've neutralized, I've added stoichiometric amounts of H plus and OH minus ions at this equivalence point. So why is my pH not 7? Well, you'll be asked that in the exam, right? It's because of something called salt hydrolysis. So this salt we've made here, this is sodium ethanoate. It actually reacts with the water. Okay, and it generates, you can see here, being a weak acid, it accepts a proton from the water to form our weak acid, undissociated as they are, and in doing so, the water becomes a hydroxide ion, and hence we have a pH greater than 7. So even though you've added stoichiometric amounts and effectively neutralize those ions, the salt you make generates hydroxide ions in solution. So yeah, weak acid, strong base, 8 to 10 is what I usually quote. And then again, if you look on this one, with this time we've got a weak base versus a strong acid. So we've got a weak base in the conical, we're adding our strong acid. And if you look at the equivalence point here, okay, you can see it's below 7 this time. And again, why? Well, in the exam, if it's 1 mark, you just say salt hydrolysis. If they want more, talk about the salt you make. So the salt we're making here is the ammonium ion, okay, ammonium chloride. So let's look at what that does in water. You can see that the ammonium ion acts as a Lowry-Bronsted base, okay, and generates H3O plus. Sorry, Lowry-Bronsted acid. An idiot. So it acts as Lowry-Bronsted acid, and what you can see is in the water, what we're generating is H3O plus or H plus ions, and therefore our pH, our concentration of H plus ions has gone up, and therefore our pH is no longer 7. So if you're asked about the equivalence point, quote salt hydrolysis. If you need to talk about salt hydrolysis, talk about the salts that you make and how they react with the water. Okay, buffers. Just very, very quickly on the buffers. So make sure you know this definition of what a buffer is. They maintain a constant pH despite small additions of H plus or H minus ions. Importantly, say small additions and constant pH. 2 types of buffer. You've got the acidic buffers. They maintain a pH below 7. They're made from a weak acid and its salt. So, for example, ethanoic acid and sodium phenolate. And if you want to talk about how the buffer works, which is quite a common question, what you would do is you'd write down the equilibrium for the weak acid, and then you can talk about what happens when you add H+ ions or H- ions. So, for example, if I add hydroxide ions, these will react with the hydroxide ions to remove them as water. And because this is a weak acid, equilibrium will shift to the right and regenerate these H+ ions. So we maintain our pH. And if I was to add H+ ions, then they would react with the salt here, and equilibrium will shift in this direction. So whatever we add in, H+ or H-, this equilibrium will shift to counteract that change. Okay. And that's why, if I just go back here, I know I'm nearly done. That's why we get this forming here. If we were doing a weak acid, strong base, so for example, ethanoic acid and we're adding sodium hydroxide, what we're forming in here is the sodium ethanoate. So we've got our weak acid and our salt being formed. Okay, that's why we get the buffer action happen. And then I'll just finish off in 2 minutes. Okay, so a basic buffer, they maintain pH above 7, and they're made from a weak base and its salt. Okay, so weak base, ammonia, as we said earlier, and ammonium chloride. And again, what we do is we write, if we're talking about how these buffers work, we write down the conjugate acid of the salt. Okay, so there's our salt, there's the ammonium ion, and we write it down as this expression here, where it's actually acting as an acid, it's a conjugate acid. And then we can talk about, if I add hydroxide ions, these are removed. Because this is a weak base, it can actually generate more H+ ions to replace them. So these will remove the hydroxide ions. And if I put H+ ions in, these will absorb those H+ ions and shift equilibrium that way. And then just finally, I'll just put that there. There's a typical exam response. Okay, to calculate your pH of your buffer, really easy. You just need to find your concentration of hydrogen ions. Okay, so you can see here I've written my expression for my acid, and I'm just going to rearrange it to find H+, as we always do. And the way I do that is I just shift the concentration of the acid to the left, okay, side of the equation, so I multiply, and then I take my salt concentration that they'll give you in the exam, okay, and I move over there. Okay, so that's how you find your H+, and then once you found H+, you can work out your pH. Or you can use this expression here. This is like a quick way of doing it, although I prefer to just work out my H+ first of all by rearranging an expression. And you can see there, I've done a quick calculation for you. Okay, I've even done the rearrangement. And you can work out HA. The HA tells you 0.150. The A-, they're telling you all this in the question. It's all up here. So you've got those values, plug them in. That's your H+, work out your pH, job done. Now, I knew there was going to be a lot on this topic. I've done quite a few more slides on this, so I'll make sure they're uploaded for you. Work your way through. I'm quite happy with where we've got to today with our buffers. That's just the quick way of doing it. I don't like that method, but it does work. So I hope that's been useful to you, and I'm going to say have a good evening, and I'll pass you back to Miss Stevens.
Thank you very much, Mr. Black. So yeah, as Mr. Black said, I hope you did find that useful. Next week's session will focus on topic 4.8, which is that very large but interesting topic, which is the organic synthesis analysis. So hope to see you all join us back next week. Goodbye.
Goodbye.